Okay, now we can have a little bit review, and I can give you maybe one or two, maybe two or three questions first, and then we can um, move further. So yeah, let me go through one or two questions. Um, Let me check the question. Okay. Okay, let me go through. Okay, find the volume generated by rotating region bounded by the given curves, the given curves about, let's say, y-axis. Okay, let me check the curves. Okay, let's say we have the curves is y equal 4x minus x squared, and then y equal x. Okay. And the other, let's say, same questions. Let me copy this. Copy, but different. Different. X-axis. So this is the first one. This is the second one. So same question, but different rotations. But for this one, we have x equal negative 3y squared plus 12y negative 9 x equals 0. Okay, let's try these two questions. Put a little bit down here. Okay. Okay, so the first one, um, the curves is y equal 4x minus x squared, and then y equal x. Okay, and the second one, x equal negative 3y squared plus 12y negative 9, and x equals 0. The difference between these two, aside from the curves, is also the center of rotation. The first one rotated about y-axis, the second one rotated about the x-axis. Okay, I'll give you a couple minutes to think, and probably you can try. Okay. So first thing, the one that is essential, as I mentioned, uh, all integrations regarding the area, the volume, and later on, right, when you are dealing with the multiple integrals later in calculus 2, or maybe later if you meet up the another subject related to advanced mathematics, uh, all integrations, it's better to visualize or imagine if you can at least sketch the basics. Sketch the basics. So my suggestion is you just need to take the sketch for the curves, okay? And I believe you need to be familiar with the sketching, especially for essential functions. Okay, essential function like polynomials, um, the trigonometric, the exponential, they are one of the essentials that you need to you can draw easily. Okay, you can draw easily from your mind, okay, and then you can translate into your sketches. Okay. Now, uh, if you look here, okay, if we take the, let's say, the 4x minus x squared and y equal x, probably we can take the drawings. Okay, we can take the drawings, and probably we can start with y equal x. That's the easy one. The line y equal x. Let's say this is y equal x. Okay, 4x minus x squared. We could have for this 4x minus x squared. We could check how the functions behave. Okay, so we have x equals 0 and x equals 4, right? Which means that this will be our root. Root means that the curve will have a or we will cross. Okay, we'll cross this point. Okay? So at x equals 0 and x equals 4, maybe 2 here, maybe 4 here. Yeah. Maybe around here. Okay. So we will have probably around like that. Maybe a little bit higher, maybe here. Okay. So the idea here, after we sketch the graph, another point that is important with this integral applications is finding the intersection. Maybe I will just erase this part, okay, just to note that what we are going to observe are the area between these two curves, okay, which is this one, the area between these two curves, okay. So let me just erase this, okay, and then the one that is important here is the intersection here. So we can take the calculations. 4x minus x squared equaling x. Okay. So of course, from what we have here, we could get a glimpse that for 3x minus x squared equals 0, right? Or we could take this as x equal. We could take x 3 minus x 0, so x is equal 0 and x equal 3. So you could say that this part here, and I think our drawing is pretty close, so I think this could be true. So this should be our x equal 3 and 3 is equal y, so 3.33 is our points in the intersection. Okay. Now the next thing, we need to rotate the area about the y-axis. So we rotate here. Let me write with different color to make differences. Okay, we rotate here, which means that all the area here is going to be rotated through this. If you want to take some mirror, you can imagine it's being rotated. Okay. Now, what would be the the best way to solve. Okay, what is the best way to solve? Can we take dy or can we take dx? It seems at some point dx or dy is doable at some point. If we take dy here, up until this point, this line here, y equal 3, up until y equal 3, this area here can be calculated, right? We can calculate easily. But up here will be different. Okay, do you get my point? Up here, we are going to have the trouble because this red curves is only one curve. Like, which one is the top and down curves? We are not sure, and if we let this becomes this is our curve here, because all this line is one curve. So there's a problem. Okay. So I believe to solve this problem directly all at once, then the method that we could do is we could just take the dx. So let me erase all this. So we could take the dx, let's say this one, okay, let's say this one. We could take the dx, and then we will have, let's imagine, yeah, if you forget, like, the one that easily to forget is what's the formulations for the volume. Let's make a shape. So we have like a cylinder, right? Like a can, right? Like your Coca-Cola, right? It has some thickness, it has height. Okay. Okay, this will be the height. Okay. And what else? What else do we need to write? So we know that this is a cylindrical shell, that we might need the radius. The radius here. And the idea for the volume for the cylinder, the hollow cylinder, is 2 pi r, the circumference, right? And then height, and then the r, the thickness. Okay. So let's write down the formulation. Okay. Let me write maybe around here. Oh, sorry. Let me write this in a more small size, maybe here. Okay, maybe writing the integrations, and then 2 pi. Now, what is the radius here? Because we are dealing with dx, so we could say that this is our variable x for the radius. We could be any numbers, right? So we can say it's x, and then multiply with the height. The height is the difference between this function and this function. Okay, so we could write 4x minus x squared minus x, right? That's the height, and then the x, and then we can say that we can evaluate from 0 to 3. Okay. Now our next step is we can just solve this, and I believe most of the calculations is not too difficult. The difficult part is to set up this, setting up the integrations. That's takes time. You need to draw, you need to find the intersections. Okay, that's the tough one. But let's continue. So we could have 2 phi x, and then this will be 3x minus x squared. Or maybe we could take this 2 pi out. Okay, and then we have this will be 3x squared and then minus x cubed. So we could write 2 pi. This will be x cubed minus x with power of 4 over 4. And then from 0 to 3. We could say, we could calculate this cube and power of 4. So 2 pi. This will be 27 minus 81, right? 81 over 4. Okay, then we can 27 and 4 is what? So 108. So this will be 27. So 27 over 4. So 27 over 4 and multiplied by 2, it should be 27 over 2. Okay. So this will be the answer for the volume. Okay. So pretty much, whenever you find the question about volume, and it asks you to rotate the area, you have two choices. You can have the disk method, okay, the full disk method, or the hollow disk method, or the cylindrical shell. This one is the cylindrical shell. Okay. Or maybe any question first. Maybe something missing from my explanations. Maybe you want to discuss more. Okay. So far so good for this one. Okay, what do you think? Yeah, I think so far so good, right? Okay. Okay. Now you can. I think I will let you time to take notes if you want to take notes. Okay. Okay, I think we can start the second questions. Okay. If you want to calculate the second questions, you can try as well. And if you find the answer, you can also add in the chat box. You can write the answer. Okay, now the similar questions but different curves and different center of rotation. Okay. Okay. So first of all, we could draw the graph. Okay. How do we graph this? This negative 3y squared plus 12y minus 9. First of all, we could simplify it and finding the roots. Okay. So we find the roots. Okay. So we will have well, we could say that we start from this, or maybe we can make it a more clear. Right? Oh, wait, why negative 12? Negative 4. 4y. Okay. So this will be resulting in y minus 1, y minus 3. Or we have y equal 1, y equal 3. So this will be the root, right? The roots. So let's draw the roots. So we could say that we have 1, 2, 3. So this is 3, this is 1. Okay, and now we could draw our graph. Okay, if you want to draw faster, let me give you a quick recap on the graphings. So firstly, I believe you are able to draw easily, very quick, this y equal x squared, right? Right? Easily. Now, if I draw like this, or maybe here in the bottom, this will be y equal negative x squared, right? We have the mirror. Okay. Now for y squared or negative y squared, we could have this is y squared. Okay, so x equal y squared, and this is negative y squared. Okay, so because we have negative y squared in our calculation here, so should be about that. Okay, and we can say that this is y, this is x, and because we are going to rotate through x-axis, I think it's obvious, right? It's obvious that we are going to use the cylindrical shell. Because if you want to take with the disk method, the problem will arise, right? We have the same curve, and then we would like to take difference from the same curve within which we are going to solve nothing, right? So we are going to take the dy as our rectangle there, so dy, and then we rotate, and we are making our cylinder like that. Okay. Okay, now since we have the endpoints, right? We have from the restriction is x equals 0, which is just here, the green one here. So we could write down our formulation for the volume. This will be related to, right? So this will be equal to the radius. Okay, and this will be equal to the height. Okay, the height is the curve itself, right? In terms of function of y. Okay, now we could write down the volume from 1 to 3 to pi. The radius is just variable y, and then multiply with negative 3y squared plus 12y minus 9, and then dy. So we could say that volume. So we could write all the variable, and we could start to integrate each one. So negative 3 over 4 plus 4y cubed, negative 9 over 2 y squared. I think we can write down here from 1 to 3. And we could have a little bit calculations. So 2 pi or even if you would like to take out 3, okay, take out 3. Let me just write this 12 over 3. So we could say 6 pi and maybe take negative to make it easy calculations. Take negative. So 1 over 4, so y over 4. And then take 3, so 4 over 3, y cubed, and take 3 over 2, y squared, to make it more easy to calculate. So this will be 81 over 4 minus 327 over 3, 936, plus 27 over 2, minus 1 over 4, minus 4 over 3, plus 3 over 2. Okay, I think we can solve this. I believe we can solve this carefully. Let's say this is 72, 27, it's become 5, 45 over 2, or 90 over 4, so we have 9 over 4, and we have 7 over 4, 12, 4, 3, 21, minus 16, so should be 9 over 4 and 6. Let me just type in quickly. Oh, it should be directly negative 8 over 3. So this should be equal to 16 pi. Okay. Okay, I think you don't need to be worried on some calculations like this. I will allow the calculators for integral. Okay, I will allow calculators. You don't need to be worried on if I give you an exam or quizzes. Okay. Any questions? Any questions so far? Okay, okay. Okay, I think we can move to just a little bit of finishing the sections. Okay, so 6.3, the cylindrical shell is finished. So we would like to move on to, it should be 6.4. It's about the work, but I will just skip that for our class because it's more likely to be conducted more in physics. So I would like to just go through 6.5, the average value of a function. Okay. Let me take you to the next section, which is the average value of a function. So 6.5. So let me write here to make it clear if you are having your textbook. So 6.4 skip. Okay. So I hope it's clear for you. And 6.5, this will be about the average value. Average value of a function. Okay. Now, if we have some data, some statistics. If you are using Excel, you're taking some numbers and putting some statistics. Let's say we have some numbers y1, y2, y3 to some n. Okay. And to make our average, the average will be y1 plus y2 plus all the y until n, and then divide by the number n, right? This is how we get the average. Okay, now if we try to look at our functions, so let y became just a function of x, okay, and we start looking at the x from a to b. Okay, let's observe this, and if we divide AB into subinterval. Subinterval means the one that we are doing in integrations. We are making some rectangle, right? And we slicing the area, right? So we take the let's say into some n subintervals. So we have some rectangles, like several rectangles, and make the rectangles more and more. Okay. So the length, the width, okay, the length for each subinterval will be equal to the b minus a divided by n, right? And if we take some sampling, okay, we take some sample points. So choose sample points. Sample points, let's say x1 with asterisk up until xn with asterisk. This is just a sample point. This is to show that it will work in any points you are taking. If we choose the sample points of x, then we have the function of each of our sample points, okay, up until our xn. So the average value, will be f x1 plus plus until we get the number xn, okay, and the average will be divided by n. Okay, I hope until this part clear enough. Okay, now since we know from the subinterval we could get the delta x as b minus a over n, okay, we could rewrite this into n equal b minus a delta x over delta x. Okay, now the average value, let's say y f average, it becomes, let me write the same equations here, divide by the n becomes b minus a divided by the delta x. Okay, let's simplify and rewrite this into much more neat looking formulations. That is okay, right, 1 over b minus a, and I will put the delta x behind, so this will be multiplied with our f x1 plus dot, let's just say xn and then delta x. Okay. And this part here is the part where we are going to evaluate the rectangle, if you remember the integration. So you could write down and simply rewrite this into our summation. Okay, so summations from sum I equal 1 to sum n of the function delta x. And precisely by using the limit definitions, we could write that limit as n approaching infinity, okay, of this summations is equal to and this is the definition of the average value. Okay, that's the average value. Okay, so I think it could be also obvious also if you are imagine the integral area under the curve. Okay, so if you have the area under the curve and then you divide with the total length of that curve. Okay, so it should have some value for the height, right? And the height will be the average number. And I think that should be easy to remember. Like here, what I mean is we have the curve, right? And let's say we have this is the let's say this is the area under the curve. Okay, we know the area as integration from AB and then fx dx. And then if we divide this area with the length from A to B, the distance AB, if we divide with that, then the result will be, if we take the area as the base multiplied by height, then if we divide the integrations with the length, it will be the height, right? So that is actually, if you get the numbers, that the numbers will be the average value of the function. Okay. And I believe it is it's a direct answer or direct questions, and you just need to put the formulations for the average value. Okay. Now, if you look more into some observations, we could connect this average value with the mean value theorem, if you remember the mean value theorem. Okay. So let me just take some time here if you want to take notes, and then we can go to the next page. Okay, so I will just start a little bit slowly, and because I know some of you are not feeling too well for study. But my suggestion is whenever you are already in a good conditions, you can try to retrace the lectures. Okay, and I'm not sure if, for example, if more and more infected cases and whenever you are not feeling well, I think you can just also let me know, okay, how many of you are not feeling well if you are in your room and you're not feeling focused on the lectures. If that's happened, then I think I could just give you some maybe additional videos like 20-30 minutes you can watch whenever you have free time to substitute your lectures. Okay, and that would be good idea if you don't really have enough or if you're not healthy enough to join the lectures. Okay, you can let me know. Okay, I think we can take it to the next page for today's. So let me just draw some illustrations to give you more insight and ideas. Okay, let's say we have a function like that. So okay, let's say this is our y equal f of x. Okay, and then this is the, let's say, let me give you some guidance. Okay, let's say this is a, this is let me write it black, a, b. If we have in the middle, we have another point c. If you look clearly from this curve, because it has really good asymmetry, okay, it's really asymmetric, then we could say that this height, we could say that this is the function of this point c, because of the asymmetric that we are already visualized from this graph. We could say that this is equal to the f average. Okay, so what could we really say about this average value is if the function is continuous, okay, on interval AB, then okay, we could say that there is a number, and we could write the number as a C. Okay, that the C is in between AB. In AB, such that the FC or the F average is equal 1 over b minus a integrations of fx dx. Or we could write down that the integrations of fx dx can be written as f average multiplied with b minus a, or we could say this is fc. Okay, we could say this is fc, because usually in mean value theorem we are going to observe or analyze which point c will be. So if you would like to know into more approach to the geometric perspective, look to the left graph. Okay, that you can see that it's perfectly in the middle and perfectly asymmetric. Then we could say that the FC is the F average. So what does it mean is, if this is like a mountain, like if this is empty, then we could fill this part, we could fill to here, right? And it's become rectangle, full rectangle, right? That's how we are describe the graph. Okay, and then I think that's it. Really short average value. I believe that will be the end of chapter 6. So I think we could also have another quiz, but I think will be next 2 weeks. I think next 2 weeks. Okay. Okay, any questions? Okay. Okay, don't forget to click the quiz, okay, for chapter 5. Once you are in, um, you need to finish the quiz. Okay, you need to finish the quiz, and you have only one chance, only one attempt. Okay. Anyone still not getting their midterm score? You can send me an email if you want to know your score. If you haven't, or maybe if you send me an email and I have a reply, please let me know. Okay. Because I think maybe sometimes it's going on to it went to the spam, or maybe something trouble in my inbox, and I need to check. Okay. Yeah, you can email me. I think I think most of the students already emailed me, and I give the reply. Okay. I think we can move to a new chapter. So chapter 7. Chapter 7 should be about the techniques for integral. Okay. So chapter 7. This is about the technique of integration. Okay. So we start with the integration by parts. Okay. To start the chapter 7, I would like to start with derivatives. Okay. So consider, let's say we have a function, a capital F like that, and we have f g. Okay, we start with from here. Okay, and then we derive. We derive with respect to x. So let all the function is function of x. So that f is f of x, g is g of x, okay, and f also f of x. Okay, so one variable. So we differentiate this these functions, and we could get, let's write the x is, you could write this will be a product rule, right? The product rule, because it's two functions, so f prime g plus g prime f, right? Okay. Now, if we let we are if we are going to rewrite this, okay, if we are going to take sometimes, and let's say we are going to write the big F into FG, okay, so let's change to FG. So let's write ddx of FG, and this will be ddx of F, and then multiply with G, okay, to make it different. And this will be ddx of G multiplied by F. So this will be the F prime, G prime, right? Okay. Okay. Now, the idea behind this is if we have this and then we take the integrations. We take the integrations to all subject. Okay. We take the integrations with respect to x. Okay. Okay. Now then we have this becoming fg, or right? It's simply completely erase ddx, right? So we will have completely cancel this. So we will have fg, okay? And this part we will have integrations g, and we still have the df because it's actually a derivative. So this will be getting df. Let me write it in terms of df, and this part we will get f dg. Okay. If we arrange the orders, f dg becomes fg minus g df. Okay. Now let's say we have some substitutions, okay, to make our calculations much more decent to be written. So let's say we have u as function of x. If we have u function of x, then our du will be function of x dx, right? If we have v g of x, then our dv is g prime of x dx, right? Okay. Now let's write all the terms. Okay, let's write in more detail. So let's rewrite this. So f is f of x, dg is g prime x dx, right? Based on our calculation here. And then equal f of x, g of x minus g of x f prime x dx. Okay, and then let's change all with u, v, du, and dv. So change all here, this, all the terms. Okay, so this becomes u dv equal u v minus integration v du. Now what we are doing here is it's a simple technique that if you have some integrations, okay, and you're not sure that you can integrate, but you are sure that your integral, the function inside, you can make at least into two functions. Okay. Now if you want, you can arrange those functions and let the one part is u and another part is dv. Hence the name is integration by parts. You take some parts of it, okay, and you arrange the order. And when you take this part, what you can do next is you take u, you take the derivative to write here, and you take dv, you take integration to get v, and you can write here and here, and you can arrange in order. And by doing that, we are going to take further and still we have integration here, but sometimes it will be an easier integral. Well, it could also be another by parts. Okay, so this is what we call integration by parts. So if you're doing from here, okay, we get some numbers or some results in here, okay, in this part. If we need to get another by parts for video here, then we are doing another UDV, UV, video. So you have some pattern. You have some something that repeat, right? You have something that repeat until you get the simplest integrations and you get the final answer. And that's you can stop and then you can get your final result. Okay. Okay, I hope you get some idea from this one. Okay. Okay. And most of the case, um, there are two techniques that widely used for most integrations. The first one is substitutions that you have in chapter 5. The second one is integration by parts. These two techniques are by far is mostly or frequently are used for solving the integral. So the techniques that are widely used. Okay, so I hope you can use it very well, and I think it's better if you are familiar with this integration. And I have some methods to help you um, calculate this integral. It's actually still integration by parts, but with some sort of arrangement. I think it will be I think it will help you to solve some problem set. Okay, I think we can start with some simple questions, some simple integrals. Let's say we can start with integration of ln x dx. Okay, this is actually quite tricky. Okay, so if you know the ln x, okay, we can derive the ln x, right? We can derive this. It's become 1 over x. But what if we integrate the ln x? Can we integrate the ln x? That's quite tricky here. So now if we look here, if you see, we have ln and we have dx. And I think it's clearly obvious that if we take the parts of these functions, okay, we will have, let's say u is ln x, okay. If we take du, it will be 1 over x dx, right? If we take dv equal dx, if we integrate this will be equal to x, right? So we can make some arrangement for integration by parts. Okay, if you take this, and we could write uv, so u and v, so x ln x, so x ln x, and then minus integrations of v and du, which is x and 1 over x dx. So it will be x 1 over x will be cancelled, and we will have only dx. And we can simply conclude that this will result in dx integration will be minus x. And don't forget to plus the constant every time you finish any indefinite integral. Okay, and that this will be the answer. So if you want to check, we can check. We can check the if this is true. we could check from derivative, right? So if we check the derivative, we will have the product rule. So ln x plus 1, right? And then this will be minus 1. So this will be 1 ln x, right? So this is true. Okay, just some easy to follow example. Okay, let me just let you take some notes for a while if you want to take notes. Okay. I think I will just give you more examples to see how we can apply these techniques of integrations in some questions. Okay, maybe we could write another one. Let me just start with a simple one so you can process and have better understanding. So if we let the integrations x sine x dx, okay, what could be the results? Okay. So the idea when you have some integrals and you want to do the integration by parts, okay. The first thing is we need to be aware of that the structure, it should be udv, right? udv, and you need to arrange the structures becomes uv minus vdu, right? This is the arrangement for integration by parts. So the first thing you need to do is you need to select, okay? Select u and dv from the function, or maybe just write select u and dv. And then arrange the integration. Arrange the integrations, which means that you need to find du and you need to find v from. So you need to find which part that you want to derive and which part you want to integrate. Okay. So by selecting u and dv, the implications is you are going to find which part that you are going to derive. Okay, u becomes du, and which part you are going to take integrations. Okay. Okay, then if we have this, okay, you have x sine x or x sine x dx. Of course, the dx part will be it will be deal with the integration. So we are just looking at x and sine x. Now, how to know which part is to be derived or which part is going to be integrated. In a short, okay, in a short summary, okay, what I can tell you is, if you see like some simple function like this, and if you see that it can be derived into 1, right? So x derived becomes 1, and derived becomes 0, right? Easy to be derived, and you get 0 with an easy way. Okay, so you could take that as your u, and the other one is sine x. Take that as your dp, because you can also argue that sine x will be just if you derive or if you integrate, it will resulting in cosine, and you try one more, it becomes sine, cosine, sine, cosine, sine, cosine. It will be repeat, right? It will have a cycle. Okay. So if we take this u and dv, then we can write. Okay, we can write. Maybe let me write a new one here. X sine x dx. Okay. So let's choosing x as u, so du will be 1, or du is dx, and v, dv is sine x dx. So when we have v, we integrate, this will be turns out to be integral sine is negative cosine x, right? So we could arrange in our structure for integrations by parts. So we could write down that x sine x dx is equal to x and then v minus cosine x, and then minus integrations of v du. So this will be minus cos x, and then du is dx. So I will write this minus cosine x as multiplied with x will be minus x cosine x. This will be plus integration of cos x will be sine x, right? And then we can take plus c. So we could write sine x minus x cos x plus c. Okay. I hope it's clear. Okay, it's easy to be imagined. Okay. And what's happened if you are maybe selecting the other part? Okay, we can still write the integrations if you would like to look on. So x sine x dx. So let the u is sine x. So du will be cos x dx, right? And dp will be x dx. So your v will be x squared over 2, right? Yeah. So if you have this, then you can write down that x sine x dx is uv x squared over 2 sine x, and then minus x squared over 2 v du cos x dx. Okay. I think the problem will be this part. You should still have some steps to write down, right? While the first method here, we could get direct answers from this part. It's easy to follow this, right? So I'm not suggesting this. Okay, let me give you a more little bit difficult from this one. Let's just write x squared sine 3x dx. Okay. Now, as usual, we should select wisely which parts that we are going to derive and which parts we are going to integrate, right? Like, and also I mentioned that you can select the parts that you are going to derive. You can select the parts that easily to be derived, and it's better if it can be getting 0. Okay. For example, the previous example, if you take this as u, so u is x, you could see that if we derive twice, it will be a 0, right? If we derive twice. And if you look here, I think if you see x squared, if you derive several times, if you 3 times derive this x squared, it will become 0, right? So I think that's the best way to observe that this is the best choice for u. So u will be x squared, that's the first one, and dv will be the other part. Because it's similar structure with before, so the how we can select is basically based on the same reasons. Okay, based on the same reason. So du will be 2x dx, right? And phi will be integrate sine 3x is negative cosine 3x divide by 3. Don't forget divide by 3. And how to know that we need to divide 3? We can imagine we derive. Okay? Then we need to have divide by 3. So we can have arrangement that is, this will be uv. Uv is x squared minus cosine 3x divided by 3. And then minus, okay, integrations, and phi du. Since phi is negative, I will take this into positive. So I will write 2x cos 3x over 3 dx. Okay, I will write this in more clear and factorize 2 over 3. So we will have another integrations x cosine 3x dx. Okay, now we still have this, and still it's the same structure as before. We could do one more time. We could select another u, this is x, another dv, which is cosine 3x. So du is dx, and phi will be negative, not negative, cosine is positive. So sine 3x over 3. Okay, and then we can write down this part, and don't forget that we still not finished the whole thing here, so we just finishing one by one here. So we could write down that this will be equal to 2 over 3 that we need to multiply with u phi is x sine 3x over 3 minus, okay, we have integration sine 3x over 3 and then the x. Okay, and then I think this is already simplified, and we can directly get the answer from here that this is equal to plus cosine 3x over 9, right? So we could write the whole integrations. Let me write the questions. This will be equal to negative x squared cosine 3x over 3 plus 2 over 3, and then multiply. Let me write this as 2 over 9. Okay. Directly write this 2 over 9 x sine 3x, and then plus 2 over 27 to this one, and then cos 3x plus c. Okay. Okay. So if you see and observe from the beginning, I hope you can get the idea of a pattern here. I hope. Okay. For this kind of structures, okay, we start with this one, right? We start with this. We get the u, okay, is x squared. We derive that. We get the d phi. We select d phi as sine 3x, and we get the integrations. We arrange the structures, and we get this. Okay, and you'll see that this is same structure or similar structure with the first original one, that you are going to take the x as your derivative and your trigonometric function as your the one that you are going to integrate, right? Becomes sine 3x here. So what if, okay, what if we could make a pattern? What if we could make a pattern that is precisely going to have, like, if we have this this integration by parts, okay, what could be if we could rewritten here in a table? Let me just write a table, and let's name this T and I. Okay, the one that is going to have D is the one that you are going to derive, which means that this will be going to be your U, right? That is the one that you are going to derive. So let's take U is here, okay? And the one that you are going to integrate is d phi, right? Okay, so derive U becomes du, and integrate d phi becomes phi. So from this table, let's multiply the first part here, multiply with positive, and the second part with negative. And then what we can do, we multiply u and phi, and multiply this, multiply phi and du. So how do we read the multiplication? So positive, multiply with u, multiply with phi. Okay, and then we can write that this is u, phi, and the second part, negative, okay, multiply with du and phi. So negative, but for the one that is equal in height, this is the diagonal one. So diagonal one, you're just writing UP. But for this one, you're writing with integrations and then phi du. Okay. So let's take this table into our method for calculations, okay, for calculating the integration by parts. Okay. Now, the only way we can do this is we are going to select which one is going to be derived and which one is going to be integrated. Okay, let's take our case x squared and sine 3x. Okay, this is the one that we are going to observe from here. Okay, so let's take, this is going to be the one that's going to be derived. This is the one that's going to be integrated. Okay, okay, let's say we derive this 2x and then 2 and then 0. Okay, and then stop there, right? And then integrate, become negative cosine 3x over 3. Integrate one more time, sine 3x, 9 over 9. And then integrate one more time, we will have cosine 3x over 27. Okay? And then multiply with positive, negative, positive, negative. Now what we can do, multiply diagonally. And the one that is the last one, multiply here, but since it's 0, then it's not necessary to multiply. Okay, so we could write that this integration is equal with multiplications, and then this will minus, so plus, and then plus 2 over 27 cosine 3x plus c. It's the same results with our usual integration by part. Okay, I think, okay, if you feel this table of di can help you, then you can use it. Okay, you can use it easily. But if not, you can just stick to the old one here. Just taking one by one. UV minus integral phi du, and all the time you can find out. Well, actually, this di table is the same thing as the integration by parts with some modifications, okay, to help calculate the repetitions. Okay, because if you see here, there is some repetition, right? Repetitions of taking the one that you are going to derive, the one you integrate. This is the same. This is also the same. Okay. Okay. Do you think it's helpful for this di table, the method? It's not on your textbook, so I hope this helpful for you. And I learned this method in high school and think for university entrance. Okay. Any questions regarding this integration by parts or my di method here? For this di method, there is no like restrictions or rules, but whenever you are dealing with the functions, maybe I will give you another more example so you can have much more insights or maybe inspirations to the idea. Okay, let me give you more on the other integrations. Okay, I hope we can skip this part. Okay. Okay. So what if we have e to the x and sine x, and then the x? Okay, you can use the old way using uv minus integral phi du. Still, you can find a way to solve through that method. Or, if you would like, we can take the. Let me start with we just taking for example, e to the x as u, and then dphi is sine x. So phi will be negative cosine x, and du is still ex dx, right? So we could say that we are going to have so still we have another one, okay? And you could try to look at up until several times. If we take another u and then we take the derivative, we take dphi and then integrations one more time, it's sine x. You see that we have now ex sine x, and then minus, okay, integrations ex phi du sine x dx. Okay. If you are not focused, okay, then you will try to do one more thing here, u dphi, and then you will do repetitions. You will do cyclings. Okay? But if you carefully stop here, okay, and you will see that the original functions in the question is the same thing as your integrations, then we can finish this. Okay, we can finish this. So we can write down. So we can write down that this is plus ex sine x minus ex sine x dx. And we can solve and place this over here, and so we can have 2. Okay. And then we can solve by divide by 2. So ex sine x dx become negative half ex cos x plus half ex sine x, and don't forget that we have plus c. Okay. Now what if we are using the di that I told you before? It will be the same. So start with the right d, right I. This is ex sine x. So this will be negative cos x, negative sine x. This is ex. So how do we stop? Okay, we could take everywhere e to the x, e to the x, e to the x. We stop where we find that this is going to be the same structure with the original questions. Okay? We have ex and sine x. This is the same structure. So we stop here. And then we multiply with the signs. We multiply here, and don't forget multiply the last one. Okay? So this will be equal to, so don't forget to write the questions to solve this tricky questions. So negative ex cos x plus ex sine x, and don't forget the last one will be minus, and integral ex sine x dx. Okay, so the last one that is on the bottom, this one, you need to write in terms of integral. Okay, and then we solve as we did before. So we are going to rearrange. We move this to the left side, and then we can solve later on. Okay. Any question? No? Let me. I'll maybe give you one more idea. Okay. What if I have integral of tangent inverse x dx? Well, I think the easiest way for you to think is if you take tangent inverse, you don't know the integral of tangent, right? So, but we know the derivative of tangent inverse, right? We can derive this. So if we take this u tangent inverse x, we could get du as 1 over 1 plus x squared, and then take the dv dx, and p is x. And we could also just try to write in the di. Still okay, I think. Still same conclusions. So we multiply, and then arrange in our uh, our structure. This will be x tangent inverse x, and then minus integrations x over 1 plus x squared dx. And we could solve this with substitutions, right? So substitute with u 1 plus x squared du is 2x dx. So dx is 1 over 2x du. So we will have half, and then we have 1 over u, right? 1 over u. And then integrate du. This will be results in half ln 1 plus x squared, right? So we could write down the calculations for the tangent inverse x dx will be equal to minus half ln 1 plus x squared, and then plus a constant. Okay. Okay, I think I will just stop until here. Uh, Actually, I prepared some feedback. Okay, so if you would like to join the feedback, I will give you the feedback. Okay, but if you want to write some notes here, you can write for a while. I give you maybe just a few minutes to write, and we can do our feedback session. Okay, okay. I think we can uh, we can continue this chapter 7 next Tuesday. But like I said earlier, like if you are not really having a good conditions for you to have lectures on the day, let me know. Okay, if you feel maybe a little bit dizzy or because of the COVID, let me know. Okay, so that I can at least, if I see that maybe if half of the class is not really going well, then I just prepare a video for you to just to watch, and you can watch like anytime you have free time. Okay. Okay. We could go to here, but let me just start the feedback, and if you haven't scanned the QR code, we can scan later. Okay. So let's start with this. So I hope you can join. Okay. Even though maybe if you're still not wait for me. I hope you can join the sessions with me. Let's wait for a while, or maybe I will check the. Check the other. Oh, I think I can share you the other one. Oh, I think we have joined it. Okay. Okay. Let me wait for a while for you to join. Okay, if you have time, if you are able to join, please join. Okay. Okay, can you join other students? Okay, 5. And then maybe you can write your name or student ID so that I will know that you are joining our feedback. Okay, I think I can start. Okay. Okay, question number 1, only 3 questions, and hopefully the time is okay. Okay, start with the first one. Okay, this is true or false. Just a 20 seconds. You need to be very quick and remember, and you could take some imaginations. You have some region revolve on x-axis. Okay. What is the volume? Yeah, it should be true. It should be true. Okay, you can discuss later on. Okay. Okay. Next question. Okay. Okay, Pam. Good. Pam. Anything, Tayam? Also good. Okay. Question number 2. Get ready. Okay. Uh, Not sure if the time is enough, but hopefully you can get the answer. You can use the symmetry. Okay. You can use the symmetry. You can use the symmetry. Okay, I hope it's clear. Okay, 20 seconds. I hope you get the correct answer. You can use the symmetry and then you can multiply by 2 at the end. Okay, 3, 2, 1. Okay, time's up. Is it correct? 9. Okay. Okay, so should be still not getting any result. Last question. Okay, get ready. It's still calculation, so I think if you are preparing some paper or maybe your iPad, we can start. Okay, you don't need to write the pi, and you can just select the option. You can just select the option. I give you 2 minutes 50 seconds. Okay. Still, we have 1 minute 40 seconds. Okay, I hope the time is uh, enough, and this is also will be my consideration, okay, for preparing times, especially for your quiz or exam. Okay. Of course, I will be thinking on which time limits that I should give. Okay. Okay. Oh, yeah. It should be the first one, the first option. Okay. So, oh, okay. So, congratulations. Okay, congratulations. Continue, right? Okay. Winning the game. Okay. Every time we have this session, I will give a bonus point for you. And of course, the other all who join the feedback also, I will consider a bonus point. So this will be the end of our lectures. Okay, I hope you are stay safe. Till we have please until uh, I hope until the first week or second week of June. Okay, that's my schedule for final exam. Okay, so thank you for joining my lectures today. I know that we are still in not really good conditions for learning. Okay, I hope you are still stay safe. Okay, still and stay healthy. Okay, I wish you better recovery if you infected by COVID. Okay, yeah, thank you
Thank
so
you,
much.
Prof.
Yeah, thank you all.